Okay, this is going to be the part 3 of the video. We're going to do example 4. Um, and we're going to look at some information about second derivative test. Real quick, if we remember about a point of inflection, that says if the second derivative is 0 and the second derivative changes sign, then you have a point of inflection. But the points of inflection are just where the graph changes concavity. So we're going to see that we can get a point of inflection without the second derivative being 0. So this theorem only holds if the second derivative is 0, then this statement here holds to make a point of inflection. But if you have a region where the second derivative is not 0 or the second derivative is undefined, this theorem doesn't really apply. You could still have the second derivative being undefined, and you could still get a change in concavity. So we're going to look at an example that's like that. So we want to find points of inflection of f of x equals x to the 5/3. So if we have 0 with the change in sign, that's a point of inflection. But if the concavity changes, even if it's not at a 0 with the second derivative, if you change from concave up to concave down somewhere, that will also correspond to a point of inflection. So let's take the first derivative. F prime of x equals, let's see, it's 5/3. X subtract 3/3. 5/3 take away 3/3 is 2/3. And then f double prime of x will be, let's see here, we bring this down. 5 times 2 is 10. 3 times 3 is 9. So it's 10/9 x to the subtract 3/3. That's negative 1/3. So we basically have 10 over 9 times the cube root of 3, cube root of x downstairs. So if we look at a little chart here, at x equals 0, our function is undefined. For the second derivative. Because division by 0 is never defined, so if we let x equal 0, cube root of 0 is 0, we have division by 0, so we're undefined there. We're going to look at negative infinity up to 0, and then 0 up to infinity. Oh, also we should note if we set this function here equal to 0, and we try to solve it to figure out, so we found out where it's undefined, but we said is it 0 anywhere? When you multiply this 9 square root of 3 across, you get 0 times 9, cube root of x, that equals 10. 0 times anything 0, so you get 0 equals 10, which is no good. So there's no f double prime of x equals 0. There's no solution to where the second derivative is 0. So we say, okay, let's think about this a little bit. If I put negative numbers in for x, the cube root of negative numbers is negative. Positive 9 times a negative number is negative. Positive 10 divided by a negative number is negative. So we're negative over the first region. If I input a positive number, so a number bigger than 0, if I input a positive number, cube root of positive is positive. 9 times a positive is positive. 10 divided by a positive is positive. So what this means is for this particular one, we have a point of inflection at x equals 0 on the graph of f, because since the second derivative is negative, that means that the base function is concave down. And over here, from 0 out to infinity, that means the second derivative is positive. That means f is concave up. So there's a point of inflection at x equals 0 on the graph of f as f changes from concave down to concave up. At x equals 0. So here's one where we didn't use the theorem, or we didn't use the point of inflection theorem because at 0 we were undefined. But we said, well, to the left of it you're negative, to the right of it you're positive. So you still get a point of inflection on the original graph there because you change from concave down to concave up. So that's kind of a weird one where it's finding the point of inflection, but since the setup, since you don't have f double prime equals 0, you can't use this theorem, but you can still, since f double prime of x was undefined, you can still get a change in sign in the second derivative. And that says your graph flips from concave down over to concave up. And that tells you that there's going to be an inflection point at that particular x value. Okay, let's look at something called the second derivative test next. Here's kind of how this works. Let's say we have a graph that's concave down. Well, if you're at the top point here, this would be, so this is on the base graph of f. So over this region, f is concave down. At the top point here, f prime is 0. This would be a critical point. So if you have a critical point and your graph is concave down, where that critical point occurs, that'll be a local max. And the reverse is true if you're concave up and you have a critical point where the first derivative equals 0. Then this right here will correspond to a local min. Because if you're not worth 0, you're positive on this side, you're negative on that side. So you only get the max or min if it falls on a critical point. So what we're going to do is we're going to write out a theorem that kind of uses the second derivative to tell if you have local max or mins, and then we'll go through and we'll do an example, and then we'll stop there, and we'll do the last example kind of in its own part. So for this one, we're going to say, all right, this is the second derivative test. Okay, so we're going to say let C be a critical point. Of f of x if f double prime of C exists, then the following things happen. We get f double prime of C is greater than 0, implies that f of C is a local min, it's a local min. If if you have a critical point and the second derivative is less than 0, that means you're concave down. So if you're concave down and you're at a critical point, that's going to correspond to a local max. And then if your second derivative at C is equal to 0, that will be inconclusive. And then you get f of C may be a local min, local max, or neither. Okay, so this is our second derivative test. What we're going to do next is we're going to analyze the critical points. So this is example 5. It wants us to analyze the critical points of f of x equals 2x minus x squared times e to the x. Okay, so first of all, we need to figure out what our critical points actually are, which to get a critical point, if you remember, it's going to be based off the first derivative. In this case, we're going to have to use the product rule, so I'm going to leave the initial part alone. I'm going to take the derivative of e to the x, which happens to be itself e to the x. Plus, now I take the derivative of the first part, which would be the derivative of 2x is 2, minus the derivative of x squared is 2x. And I'll leave the e to the x alone. I'm going to simplify this algebraically, so I'm going to factor these e to the x's out. I get 2x minus x squared plus 2 minus 2x times e to the x. So basically we factor the e to the x out, and the rest of these combine together in a single line. Let's see, what does that tell me? 2x and negative 2x cancel, so I get basically 2 minus x squared times e to the x. This is never undefined. If I look at where this thing equals 0 to figure out the critical points, I'm going to set f prime of x equal to 0 to try to find the critical points. Because this isn't undefined anywhere, so critical points are where the first derivative is 0 or where it's undefined. This is not undefined. Also, we should note e to the x is always greater than 0, so it's never actually equal to 0. So the only places where my first derivative is going to equal 0 is where 0 equals the first factor here. So I get x equals plus minus square root of 2. Okay, so I have negative square root of 2. And then out here I have positive square root of 2. And for my first derivative, we're 0 at those points. So to use the second derivative test, if we were using the first derivative test, we'd get the intervals, we'd compare the interval, and we'd look, are we negative changing to positive, or are we positive changing to negative? And the first derivative test, we could figure out if we're a local min or max that way. The second derivative test is just going to determine whether the second derivative is positive at negative square root of 2, or whether the second derivative is negative or positive at positive square root of 2. So let's get the second derivative. This right here is my first derivative, so I'm going to take its derivative to get the second derivative. So f double prime, we have to use the product rule again. We'll leave this alone. Take the derivative of e to the x, which is itself, plus, now I take the derivative of this, the derivative of 2 goes away, the derivative of negative x squared is negative 2x, and then e to the x stays the same. We're going to factor that out. So factor those e to the x's out like we did earlier. We get 2 minus the 2x minus x squared times e to the x. E to the x is always positive. So I'm just going to see, does negative square root of 2, if I put that in for this, does that make this part here positive or negative? So when I put negative square root of 2 into that, I get 2 minus 2 times negative square root of 2. Oops. So 2 minus 2 times negative square root of 2 minus negative square root of 2 squared. And I get a positive number back, so it looks like I'm positive here. And now I'm going to see, so when I put negative square root of 2 in, the bracket becomes positive, e to the x is positive, which says I get a positive value back. When I put square root of 2 in, I get 2 minus 2 times square root of 2 minus square root of 2 whole thing squared. I get negative 2.8, so it's negative times a positive says we're negative. So we're negative there. So from my chart, I have my two critical points. My second derivative is positive at one of them. My second derivative is negative at the other. So if the second derivative is positive at a critical point, you have a local min. If the second derivative is negative, we have a local max. So we're going to have a second derivative is positive, so we're going to have local min here. We're going to have a local max there. And we just need to write it up nicely. Let me scoop my second derivative here, just kind of over to the side. And we'll write up the answer down here. So we're going to say f of negative square root of 2 is a local minimum as x equals negative square root of 2 is a critical point and the second derivative is greater than 0. So for a critical point and the second derivative is positive, it's a local min. So to finish this up, we'll say f of square root of 2 is a local max as x equals square root of 2 is a critical point and the second derivative is less than 0. So second derivative is negative. So we used the second derivative test and we were able to analyze whether the critical points were local maximums or local minimums. So we'll stop on part 3 there.